Okay, I think we will get started with the webinar. Thank you to all the attendees for coming here today. Um, this webinar will be about known sources of continuous gravitational waves and how we can understand neutron stars with them. So yeah, if we move now to the next slide, I just want to introduce everyone who's going to be speaking here today. First, we will have an introduction by Professor Ian Jones from the University of Southampton in the UK. Then we will have a discussion about known pulsars from Petros Verma, who's a PhD student at the National Center for Nuclear Research in Poland. Then we will have a small talk about supernova remnants from Lucy Strang, who's a PhD student at the University of Melbourne in Australia. And then we will finally have a talk about accreting neutron stars by Andres Vargas Sanchez, who's also a PhD student at the University of Melbourne. And I'm Andrew. I'm a postdoc at the Université Catholique de Louvain in Belgium, and I'm the moderator for this webinar. And we are lucky to be joined by panelists who can help answer questions that you all may have during and after the webinar. Win Ho from Haverford College in the US, Simone Mastrogiovanni from Observatoire de Côte d'Azur in France, Aranuva Mukherjee from Saha Institute of Nuclear Physics India, and finally Amy Hewitt from Lancaster University in the UK. And if we move now to the next slide, I just want to then just give a brief overview of how international this collaboration is. So you can see here, plotted on the map of the Earth, is all the different detectors that we have. Both LIGOs, GEO, Virgo, and KAGRA, and as well as orange dots that correspond to the places where people in this webinar are based right now. And so you can see this collaboration is very international. It's very multidisciplinary, and it's a great collaboration. And I also just want to take this time to thank all the people who have worked tirelessly on the detector, computing clusters, etc., all throughout the COVID-19 pandemic. And we would not be sitting here today with results if it were not for these people. And so now I will move to the next slide and give it over to Ian for the introduction. Thank you.
Okay, well, thank you very much, Andrew. Yeah, so my job is just to set the scene a little and talk about the astrophysics of the sorts of things we'll be discussing today. I suspect many of you know this anyway, but the gravitational wave, what is it? Well, way back in 1916, Einstein, with his theory of general relativity, realized that when objects move around and their gravitational field changes, those little changes in the gravitational field themselves propagate as waves at the speed of light. And that's what's shown on this picture here, two stars in orbit around one another, swirling out gravitational waves. If you put the numbers in to Einstein's theory, you quickly realize that the strongest gravitational waves are produced by violent astronomical events. And this slide shows the four classes that we often divide these sorts of things into. Top left, it's that same picture as the last slide. It's two compact stars, so two very small massive stars like two black holes or two neutron stars, which is another sort of very small heavy star, in orbit around one another. As they orbit, they produce these gravitational waves. Those gravitational waves carry off energy, the orbit shrinks, and eventually the stars collide. Now, we've actually seen about 90 events like that with our gravitational wave detectors. And there have been some previous webinars in which we've talked about those results. But there's a lot more that we would like to see. If you look at that top right picture, that's the picture of the aftermath of an explosion. So this is when a star has reached the end of its life. Its outer parts have exploded, but its inner part imploded. This happened back in the year 1054, and we think even Chinese astronomers saw this happen. When that happens, when the core collapses of the star, you could get some strong gravitational waves from that supernova core collapse. So we've not seen that, but we'd be interested to see that. Bottom right, this is a famous picture. It's a picture of the electromagnetic microwave background. This is some electromagnetic radiation left over after the Big Bang. It tells us what the universe was like when it was about 380,000 years old. We haven't, but we'd love to see the gravitational wave analog of that. And that would tell us about the state of the universe when it was just some fraction of a second old. But what I really want to concentrate on is this bottom left picture. This is what this whole webinar is about. We're interested in detecting very, very long-lived sources of gravitational waves from probably spinning neutron stars. So a neutron star is a small dead star. It's what you can get when a normal star explodes, like the thing that happened top right, where you get something like the mass of a sun compacted in a small volume, and they can rotate fast. This is what I want to talk about next. We've not seen with gravitational waves any of these things yet, but we hope to, and we're looking hard, and that's what we're going to tell you about. So on this next slide, I want to do a bit of a compare and contrast. I want to compare what we have seen and what we've from these binary star systems, from these stars colliding, with what we're going to talk about in today's webinar, these so-called continuous waves, which last a long time. If you look at the top half of this slide and top right, there's a little schematic picture of what we saw with our first ever gravitational wave detection back in 2015. We had two black holes. They started off far apart. They gradually got closer and closer and eventually merged. And the signal they produced, well, it got stronger and stronger, higher and higher in frequency, and then disappeared when the two stars finally collided. There isn't a timeline there, but this whole thing happened in about 0.3 seconds. In contrast to that, what we're talking about today are very long-lived signals that could last years, centuries, possibly even millions of years. And so these are relatively weak signals, but because they last a long time, we think we've got a shot at detecting them. And whereas you get this short sort of violent signal from the binaries, what you can see at the bottom right here is it's basically a sine wave, so an oscillatory wave that goes on with very little change for a long time. So that's the sort of signal that we're trying to detect today. So next slide. So these continuous wave searches, as we call them, continuous because the waves go on for a long time, are tricky. And the way in which we actually do them depends on how much prior information, how much advanced information we get from our colleagues in electromagnetic astronomy. And we talk about 4 different sorts of continuous wave searches. There's a plot bottom right here that's got 2 axes on it. The horizontal axis is how computationally costly a search is. So searches that are really easy to do and you could do on your laptop would be on the left. Searches that you need a huge supercomputer for would be on the right. And then the sensitivity of the search, basically how weak a signal that we can see. So very sensitive searches would be at the top, relatively poor searches at the bottom. So targeted searches, these are searches that are really cheap to do, and they search very deeply. And this is where we're looking for a signal, say, from a known neutron star, where our colleagues in electromagnetic astronomy have told us where it is and how it's spinning. So basically, we know almost everything that we need to know to go looking for our signal. The next most difficult in terms of computational cost are the narrowband searches, where typically we know, say, a sky location like a supernova remnant or a little patch like the galactic center, but where we know, say, where a star probably is, but we don't know how fast it's spinning exactly. And so what we do then is we do a search over a little small frequency band. So it's a bit more expensive than a targeted search and doesn't dig quite as deeply into the data. Then the most difficult sorts of searches that we'll talk about today are the so-called directed searches. This is where we know a sky location, but we haven't got any idea what sort of frequency we should look at. So we have to search over a frequency band of order hundreds of hertz. And these are very computationally costly indeed. Then the last sort of search that we won't talk about today are so-called blind searches, where we know nothing. So we're searching over all the directions in the sky and over all frequencies at once. You could easily saturate the entire computational power on the planet doing one of these searches. We had a recent webinar a month ago on this, and there's a YouTube link there, so by all means click on that. But today we're talking about where we basically know where we're looking in the sky, but we don't always know quite what frequency to look at. And one of the tricks that we use to make life a bit easier when doing these searches, and it will be described just very briefly later by my colleagues, is that we sometimes chop the data up into little bits and analyze the little bits separately and combine them together. But the basic message here is these are difficult searches to do. You need lots of computing power, and how much you need depends on how much information you've got in advance. So what do we think produces these long continuous waves? Well, our sort of leading candidate is a spinning neutron star. So a neutron star is a small dead star, very heavy, mass of the sun in something like the radius of a city. That's what's illustrated with that little sort of Google map image that you can see top left. They're very dense. They're denser than atomic nuclei, so we would love to learn about them from gravitational waves. If the star is perfectly spherically symmetric, or if it's perfectly axisymmetric and spinning, it won't emit any gravitational waves. But if it's deformed in some way, then it will stir up its gravitational field and it will emit some gravitational waves. And the way that we think about this is we're slightly naughty and we use the term mountain. It's not really a mountain like Mount Everest. It's more like a sort of a global change in shape of the star, pulling it out like into a shape of an American football or a rugby ball or something. And we say that if the star's spinning about the z-axis in this picture, but it's say longer along the x-axis than the y-axis, then it's non-axisymmetric. So it would produce gravitational waves. Its gravitational field would vary in time. And we introduce a little dimensionless number epsilon that measures how non-axisymmetric it is. And it's basically a measure of how different the components of the moment of inertia tensor are. Moment of inertia tensor is basically just an object that measures how mass is distributed about the x, the y, or the z-axes. We don't know how big these mountains are likely to be. Some theoretical modeling indicates they might be like 10 to the minus 6, or 1 part in a million, but we're not too sure. Anyway, a wave that has got a mountain and is spinning will emit gravitational waves, and it turns out they come out not at the spin frequency, as you might have naively imagined, they come out at twice the spin frequency. So really, we're going to be talking about looking for these sorts of signals now. We only expect to be sensitive to these sorts of things in our galaxy. Spinning neutron stars in other galaxies are probably, not definite, probably too weak to detect. And there might even be some that we don't know about at all from electromagnetic data. But as I say, we're concentrating more on systems where we know where to look in the sky. Before I wrap up, as well as having spinning neutron stars with mountains, neutron stars themselves, they're called neutron stars because they're mainly made of a neutron fluid. And whenever you've got a rotating ball of gravitating fluid, you can get waves in it. And this is a real picture of a wave, a Rossby type wave, as it's called on the Earth. We expect and we hope that there'll be similar sorts of waves existing on neutron stars. They change the gravitational field too, so they too could produce gravitational waves. So some of the things that you heard from my colleagues in just a moment, we'll talk a bit about this sort of gravitational wave emission as well. So that's it. That's all I wanted to say. So I'm going to hand over to my colleague Paritosh now, who's going to tell you about gravitational waves from known pulsars.
Thank you very much, Ian. So I'll talk about continuous waves from pulsars. Next slide, please. Okay, so pulsars are a special kind of neutron stars, which have very high magnetic field and they are spinning at a very high speed. So we can consider a pulsar as a dynamo with a strong magnetic field. As this dynamo rotates, the change in magnetic flux induces a voltage. If we somehow measure the voltage between the pole and the equator, it comes about to be 10 to the power 18 volts. This voltage gives rise to a strong electric field, which helps in accelerating the charges. Since the magnetic field is very strong near the surface, these charges cannot cross the magnetic field lines. Rather, they are trapped and they move along these magnetic field lines like a bead on a necklace. Since they are relativistic particles, the radiation is confined in a cone, and the opening angle of the cone is determined by the velocity of these particles. And since the radiation is relativistic, it is a non-monochromatic radiation and it is linearly polarized. So you can see it on the picture, and if the spin axis is not aligned with the magnetic axis, you will get a lighthouse effect. In the plot below, there is a plot which gives the pulse profile of a pulsar. The distance between two pulses is the time period between the pulses, which indeed is the rotation period of the neutron stars. So neutron stars were first predicted in 1934 by Walter Baade and Fritz Zwicky, and they were first detected by 1967 by Jocelyn Bell and her PhD supervisor. Next slide, please. Okay, in this slide, we give the estimated magnetic field of a pulsar, which is proportional to square root of P times P dot. P is the period of the pulsar and P dot is the first time derivative of the period. For a standard pulsar, the magnetic field is about 10 to the power 12 Gauss. For an accreting pulsar, it is 10 to the power 8 Gauss. And for a magnetar, which is a very strongly magnetized pulsar, it is 10 to the power 15 Gauss. And the rough approximation of pulsar's age is given by a characteristic time scale, which is p divided by 2 peak dot. And as seen on the left plot, young and strongly magnetized are on the top right hand side of the plot, whereas old and weakly magnetized are on the left corner on the bottom side. Next slide, please. So, as I told in the first slide, these accelerating particles, they radiate the electromagnetic waves, and they come across all parts of the electromagnetic spectrum from radio waves to gamma rays, and we detect these signals using various telescopes and satellites. For instance, Parkes Satellite Telescope, Radio Telescope in Australia, Lowell Radio Telescope in Britain, and Fermi Gamma Ray Satellite. Next slide, please. Now I'll talk about gravitational waves from pulsars. As said by Ian, this signal with duration longer than the typical observation time of a detector. It is believed that our Milky Way contains billions of neutron stars, and we have already detected more than 3,000 of them using the electromagnetic spectrum. And a fraction of these neutron stars, they are even emitting gravitational waves which lie within the sensitivity band of our detectors. So these signals are very weak, but they are always present. And hence, we can implement procedure to increase the signal to noise ratio because it is directly proportional to the square root of the time period. Before I move further, I want to give two definitions. The first one is the spin down. So as we know that electromagnetic radiation and gravitational radiation, they take away energy and angular momentum from the system, and hence the pulsar slows down, which means its frequency decreases and the time period increases. This is known as spin down. And what is the spin down limit? The rate of change of rotational kinetic energy is equal to the power emitted by gravitational waves, which means we assume that the entire energy, kinetic energy, is converted into the gravitational wave radiation, and we get the maximum amplitude that can be emitted by a pulsar. This is a hypothetical amplitude, by the way. Okay, next slide, please. So to search for the gravitational waves, we implement three models in our pipeline. The first one is known as single harmonic model. It is an ellipsoid with a mountain as said by Ian, and it is spinning about one of its symmetry axis, and it emits gravitational waves at twice the spin frequency. The second model is that there is an angle theta between the symmetry axis and the spinning axis. And in this case, gravitational waves are emitted at two frequencies. One at once the spin frequency and twice the spin frequency. And these two models are due to the time varying quadrupole moment. Now we have implemented the third model, which is a new theory of gravity, that is Brans-Dicke theory of gravity. And here the most dominating radiation comes from the dipole radiation, and it is emitted at once the spin frequency of the pulsar. Next slide, please. So here I present the analysis and result for our targeted search. We searched for 236 known pulsar during the O2 and O3 observing run, and 168 of them were in the binary system, whereas 161 were spinning with a frequency greater than 100 Hz. And we could not find any gravitational waves found both in general relativity as well as Brans-Dicke theory. But we improved the limits on the signal amplitude, and even 23 pulsars surpassed the spin down limit, which means they were younger pulsars and they were spinning very fast. And we obtained stringent limits on the height of mountains, as said by Ian. Okay, next slide, please. Here I present the result for two important pulsars. One is the Crab and the second one is Vela. So for the Crab pulsar, glitch occurred. I'll talk about glitch in a couple of slides after this. And there was no glitch in Vela pulsar. Glitch had a very high spin down, whereas Vela has a very high spin down limit. And the gravitational wave contribution in Crab pulsar is less than 0.009% of the spin down, whereas for Vela pulsar, it is 0.2% of the spin down. If you see the number below, this gives the 95% credible limit on amplitude, quadrupole moment, as well as ellipticity. And the numbers in the parenthesis means we perform this search using restricted orientation, which means inclination angle 1 no. Next slide, please. In this slide, we plot amplitude for single harmonic analysis, the gravitational wave amplitude for 236 pulses. The pink line gives the joint detector sensitivity of three detectors during O3 run. Blue stars are H0 amplitude and gray triangles are spin down limit, and the equation above gives the amplitude in terms of astrophysical parameters. This was done using Bayesian analysis for single harmonic analysis. Next slide, please. And here we present the ellipticity for the same 236 pulsars. The equation of ellipticity is written in terms of astrophysical parameters. So from Bayesian analysis, we get a quadrupole moment, which in turn imposes a constraint on ellipticity. Next slide, please. Okay, so we talked about targeted search. Now we'll see what a narrowband search is. So for the targeted search, we look at a specific frequency that is twice the spin frequency of the pulsar. But in the narrowband search, we give a little bit of relaxation. Instead of looking for a frequency at a given real number, we look for a frequency in a small domain which is centered about this real number. And hence, we look for a broader frequency range. We use two different methods for this search. One is 5n vector search, and the second one is F statistics. On the right hand side, you can see the plot for our searches, and the paper has already been published. Next slide, please. So, as I told before, due to the emission of gravitational waves, the pulsar spins down, but sometimes due to internal mechanisms, there can be sudden rise in the frequency of the pulsar, and this is known as pulsar glitch. So unlike continuous waves of transient signals, they have a specific start time and they have an effective time lifetime, which is given by tau. And on the right hand plot, you can see the glitch profile for Vela pulsar. And to study these signals, we multiply a continuous wave signal, which is there for a longer time, by a window function. You can see like a square wave on the bottommost figure, and the result we get is the transient continuous wave signal. It has a specific start time t0, and the duration of the lifetime is tau. And next slide, please. Okay, and here we present the result for the transient search for these pulsars. And H0 in the bottom gives the equation for the amplitude. Here D is the distance between the pulsar and Earth, G is gravitational constant, C is the speed of light, I is moment of inertia, tau is the duration of the signal, delta FGL is the frequency rise, and F is the initial frequency. So to summarize, we have not detected any gravitational signal in the O3 run, but we obtained very good upper limits, and we are very much optimistic about detecting them in the near future. And if we do so, these gravitational waves will help us to understand the complex nuclear physics that is going inside the core of these mysterious objects. Now, my colleague Lucy will talk about supernova remnants. Thank you very much.
Fantastic. Thank you for that. So we just heard from Paratosh a great summary of how we look for continuous gravitational waves from neutron stars, where we can actually see both the sky location and we know how quickly the star is rotating. One other kind of search we can do is where we know the sky location, but we don't actually know anything about the star is rotating, so we have no idea what frequency we're looking at. So if we go on to the next slide, we should see a image, a false color image of a supernova remnant known as Cassiopeia A. And I chose this image as an example of a target we've actually looked at recently. Now, each of the different colors in this image refer to different observations from electromagnetic telescopes. And this is a core collapse supernova remnant. So a core collapse supernova is what happens when a massive star more than 8 times the mass of the sun dies. The outer layers get blown off as all of the lovely colors we can see here. And if we go to the next slide, we'll get a nice little zoom in showing us the only thing I personally care about, which is the neutron star. And that's that tiny blue dot that we can see in the center of that circle, which is a steady X-ray source. So this is useful for us because it's a lot easier to find something as big and bright as an entire supernova remnant than it is to find just a single neutron star on its own. But because it's just a steady X-ray source, there's no pulsation, so we don't know what frequency we're looking at. What we do now is a directed search, which means we need to be somewhat clever about searching as many frequencies as possible. So if we go on to the next slide, I think we'll be introducing the paper we released late last year, which actually targeted 15 separate young supernova remnants for continuous waves. We looked at 15 of them because we haven't actually detected continuous gravitational waves yet. And we don't know if we expect all of these supernova remnants to emit gravitational waves, or if we only expect some subset of them to. So we try and search all of them, and we in fact search all of them. We search them 3 separate times using 3 separate signal models. When I say signal model, you can think of this as a hypothesis for what the actual physics going on is. One of them is quite a standard signal model similar to the spin down that Paratosh told us about. One of them is a little bit looser and allows the frequency to wander randomly. This means that if there's something going on that's a bit surprising, then we'll have some space to work there. And then lastly, we had one that looked at if you had a neutron star that was both spinning and precessing, in which case we'd see gravitational wave emission at 2 frequencies. That said, we still don't know what those frequencies are, so we nominally have to search between 10 and 2000 hertz. And if we tap on the next slide button, we should see an example of one of the targets we looked at, which is G189.1 plus 0.3. And while that's the name we use for it in papers, that doesn't exactly roll off the tongue. So I'm going to borrow a colloquial name for it here, which is the Jellyfish Nebula. We chose this as a target because it's both young, and by young I mean it's between 3,000 years, so younger than the pyramids, and 30,000 years old. We're going to go with 3,000 years and be really optimistic. And it's only about 5,000 light years away from Earth, so it's practically next door. And if we tap the next slide button, we should see the only part again that I care about, which is instead of all of these beautiful wisps of ejecta, there is a tiny X-ray dot, which is our compact source, our target neutron star. Now, I mentioned we don't know what frequency this is rotating at, but we do know what the gravitational wave strain could be. So I've got a formula here, and if we can just quickly run through this, H is the symbol that we like to use to quantify how loud the gravitational wave signal is. And that's going to be less than this expression on the right, where D is the distance, that's 5,000 years. Big G is the gravitational constant. C is the speed of light. I is the moment of inertia. That's something that tells us how mass is distributed around the axis the neutron star is rotating about. And this T, fans of the Greek alphabet will recognize that as tau. That tells us what the age is. So you can see that the younger and closer these things are, the better it is for our search. And we looked at, when looking at this source, we found absolutely no continuous gravitational waves. But if we go on to the next slide, we can start talking about setting some limits and constraining some interesting properties. So again, we have that formula. And if we tap next slide, we should see a little pink arrow popping up, pointing out where this appears on the formula on the right. In this figure on the right, we have the frequency on the horizontal axis. And for this particular target, we were lucky enough to be able to constrain our target space from just about 10 hertz to 600 hertz. So we didn't have to do the full 2000. And the vertical axis is the gravitational wave strain that we could hope to detect with about 95% confidence. So anything quieter than this, we're probably going to miss it. Anything louder than this, we should have seen it. The pink line represents the loudest we could have expected from this source. And the good news is we're below that. So that means we're actually starting to constrain the physics of what this source looks like. We have 2 kinds of constraints here. If we tap next slide, we'll see a comment about doing injections. What I mean here is we get the LIGO data, and once we've decided that there's no gravitational waves there, we inject fake signals into that data, try and recover them. And based on that, we can set limits. And we've done that in this image for 3 detectors, but just one of the signal models. We have the limits for both the LIGO detectors, Livingston and Hanford, signified by L and H. And we also have the Virgo detector, that's the one I think based in Italy, labeled with the V. And then to get the sensitivity in the full band, instead of melting a supercomputer trying to do it across that full frequency range, we actually just infer based on the LIGO noise curve. So we can go one step further than this. If we go on to the next slide, we'll begin talking about ellipticity. This was mentioned earlier, and we were talking about the shape of the neutron star and how spherical it was compared to how football shaped it was. Now, theory tells us that we don't expect them to have a higher ellipticity than a dimensional 10 to the minus 6. As we can see in the figure on the right, we're getting below that for 3 separate targets. We have, again, frequency on the horizontal axis, the maximum ellipticity we could have detected on the vertical axis. The solid curves represent the best guess estimate for our constraint. And by best guess, I mean most optimistic. Because it turns out our friends who do observations with optical and X-ray light don't actually agree on how far away some of these supernova remnants are. So we say we're going to take the most optimistic guess and we're going to make that our primary estimate, but we'll show in the shaded region the full range of uncertainty so that if it turns out that it's actually further away than we thought, we can still make a statement about the shape of this neutron star. We can do the exact same thing for those R modes we heard about earlier. These were the Rossby waves that are similar to what we see on Earth, except instead of being on the scale of climate systems, I don't know if it's not the next slide yet, just for me or for everyone, but we should see instead of Rossby waves for the entire Earth, we're just going to have them very, very small. About 10 to the minus 3 is the largest we could theoretically expect, but that's still loud enough to emit continuous gravitational waves. And we've, again, managed to constrain this below the limit. This is great because, again, going on to the next slide, this is going to be, we can say this for actually 15 targets, and we can constrain how loud the gravitational wave signal was. And from that, we can talk about both the shape and the oscillations within the star. Because we can do this for a number of targets, we're actually able to make some very strong statements about the physics of neutron stars in general based on what we didn't detect. And we hope that as we further tweak our algorithms and we manage to collect more data, we'll be able to either constrain that further, or if we're very lucky, maybe even make a detection of continuous gravitational waves. Now, the last thing we have to talk to you about today is a slightly different scenario, where instead of an isolated pulsar, as we heard from Paratosh, or an isolated neutron star surrounded by a supernova remnant, we're going to be looking at a neutron star with a binary companion, and that affects the way these systems evolve. I'm going to hand over to my friend Andres for that discussion. Thank you.
Thank you very much for that introduction, Lucy. So I'll be talking about gravitational waves from accreting neutron stars. So moving on to the next slide. To properly understand these targets, we first have to define what is accretion. So this is the accumulation of matter, generally gas, due to gravitational interaction. And the infalling matter releases gravitational potential energy as X-rays. So low mass X-ray binaries are binary systems composed by a donor which accretes matter onto its companion, that is a compact object, such like a neutron star, a black hole, or similar. So to the right, we have an artist's impression of a neutron star with its companion. You can see the red star accreting mass, creating that beautiful disk around the central object, which would be a neutron star in this case. Now, moving on to the next slide. Now that we know the source, what do they have to do with gravitational wave generation? Well, the accretion will create a torque that spin ups the neutron star, and if there is no spin down to keep this in check, the neutron star will break eventually. Although when we do the measurements of the frequency of these such stars, they are spinning at frequencies far from the breaking frequency, so that means that there must be a mechanism that spins them down. And we can imagine that this mechanism is a gravitational wave emission. So this idea, we usually refer to it as torque balance. Now, to put all of these together, if we move to the next slide, we have a video. So here you can see the red star accreting onto its companion, creating this disk, which should be accelerating the central star. And the way to spin down would be to generate these ripples in the space-time, which you can see. And those are the type of signals that we are trying to look in these searches. Now moving on to the next slide. Now that we know the source that we want to search, the idea is to find where in parameters to try and search for these waves. So as we have mentioned previously, these gravitational waves are emitted at certain multiples of the spin frequency, and also the signal amplitude, h naught, assuming torque balance, depends on the X-ray flux of the source, that is the amount of X-rays, and also on the spin frequency. So an ideal candidate would be one where we have measured the spin frequency or has a considerable X-ray flux, or a combination of both of those. So these kind of searches can be either a narrowband if we know the spin frequency, or can be directed searches when we don't know the spin frequency. Given the chaotic nature of accretion, these gravitational wave, we should expect them to wander slightly throughout the search, so that adds another layer of complexity into our problem. And also, as we're handling a binary system, we have to take into account the binary motion, and this is done through 3 orbital periods, orbital parameters, which are the projected semi-major axis, which you can see in the image to the right, the time of ascension, which is a reference time of where the star was at some point, and the system orbital period. Now, moving on to the next slide. We'll be talking about 2 searches we have done for these systems in the latest O3 data. The first is the Scorpius X-1 search, which involved the Viterbi pipeline, and also in a future paper, the cross-correlation search. And we'll also be talking about a search for 20 accreting millisecond X-ray pulsars, which involve the Viterbi pipeline. Moving to the next slide. So the first search we're going to talk about is the Scorpius X-1. So here, Scorpius X-1 is the brightest source of X-rays apart from the sun in the sky. So it checks the high X-ray flux that makes it an ideal candidate, as we suppose it's emitting strong gravitational waves. But it does come with some caveats, and that is that we don't know the spin frequency, as it hasn't been measured. And additionally, the orbital parameters for this system have considerable uncertainties. So that means that we'll have to search a broad parameter space to try and find a signal. And this can be very computationally challenging. For instance, this search took around 6 months in a supercomputer using in average 100 GPUs to be done. So it's quite thick. And we use a binary hidden Markov model pipeline, which allows for the spin wandering, given the chaotic nature of accretion. So moving to the next slide, where we have the results. So this search looked throughout the 60 to 500 frequency range to try and find a gravitational wave. The search yielded 35 candidates, and none of them survived the vetoing procedure. That is the step in between trying to discern if it's a signal or maybe some artifact or fluke or noise in the data. And when this happened, we calculate upper limit estimates on the signal amplitude, as Lucy also mentioned in her presentation. So you can see the results in the right. So we have in different colors the different upper limits depending on the polarization of the wave. And in red, we have the estimates, the theoretical estimates of torque balance for the best case scenario. As you can see, at least in the for the orange line, that is for the inclination angle of 44 degrees, from 60 to 100 hertz, this line already dips below the torque balance. So this means that we are already searching or exploring an area where a possible gravitational wave could be. So maybe in the future, with more sensitivity in the detectors and in the pipelines, we might find something in the future. Now, moving to the next slide. We have the search for the 20 AMXPs, which is a very new search, first time done in the LIGO collaboration. So in this case, the appeal of the search is that we know the spin frequency of the targets and the orbital parameters very well. So that means that these can be done in narrowband searches, which are not so computationally costly. So this search had 3 narrowband subbands centered at 1, 2, and 4/3 of the spin frequency. It included some targets that had never been searched before, so that is quite new. And also it included an additional target of opportunity, SAX J108.4/3658, which was in outburst during 1 month of the observing run. To the right, we can see the table with the targets. Moving now to the next slide. So as I said, this is a new search. It yielded 16 candidates, none that survived the vetoing procedure. So upper limits were estimated for many of these candidates. Some of these upper limits were new, as none of those candidates had been searched before. And using the upper limits, we can also estimate astrophysically interesting data, as for instance, the ellipticity of the neutron star or the strength of the R mode, which is parameterized as alpha. To the right, we have a diagram of a very interesting candidate, where in colors we have the log likelihood that it is a signal given a frequency. And we have in the Y the declination, and in X the right ascension. So this target was very interesting as it survived many of the vetoing procedure. However, it failed in the last veto, which was trying to see how it looked like depend on the position. And as you can see, even when you move away from the target, which is positioned in the center, you obtain high log likelihoods when you should expect them to drop. So this was a search with many interesting results, and many which are new. I'm sure that in the 04 search, we will see brand and new physics out of this. And now to finish, I'll handle this back to Andrew for the summary.
Thank you, Andres. So yeah, as Andres said, I will just summarize that this has been a webinar about known sources of continuous gravitational waves, and that spinning and oscillating neutron stars may emit long-lived quasi-monochromatic gravitational waves. And so, and throughout all of these searches, we've had many possible candidates, but have not yet been able to claim any detection. And but not all hope is lost. 04, the next observing run of LIGO Virgo and KAGRA will start at the end of this year, where we hope to have a great improvement in sensitivity and actually be able to make physical statements and make a detection about from gravitational waves from these objects. And here listed on the slide are the different papers that have been published about this, all the work that you've heard today, as well as the science summaries, which are geared towards people with a non-scientific background. So with that, thank you all for attending. And I think at this point, we are very happy to take many questions. We have a lot of time. So perhaps we could start with the question by Gabriela Conde Saavedra. Aranuva said that he can answer this question live. So maybe that we can begin with this.
Hi, Gabriela. So here is the question. Question is why the magnetic field of an accreting pulsar is smaller than the magnetic field B of a standard one. So there are a few reasons. The couple of primary reasons are the following. One is that these accreting pulsars are generally found in very old systems. By the time they start accreting matter from the donor star, it's already pretty late in the evolution phase, fairly delayed in the since their birth, quite a few billion years. So, and by that time, the magnetic field starts decaying due to various processes internally within the neutron star. For example, a simple ohmic decay will be able to reduce the magnetic field strength. Another important phenomena can also contribute to this. So as you are accreting matter from the donor star, matter comes and falls on the surface of the neutron star, and these are the plasmas. which tend to suppress the surface magnetic field, the field that comes out of the neutron star's outer surface, So what we actually observationally see can be much weaker than whatever actual intrinsic magnetic field is within the neutron stars.
All right. Great, thank you, Aranuva. And it seems that Huri Ziapor has asked a question: is the sensitivity of 04 and 05 sufficient to detect, for instance, continuous gravitational waves from supernova remnants? So we will hand this question off to Lucy, who has talked about this extensively. So Lucy, please go ahead.
Great. So I would love to be able to say yes, but the strongest I can say is maybe. So when we looked a little bit earlier in the slides, we saw some plots about what parameters we could have for the ellipticity or the amplitudes, which tell us how loud we expect the gravitational wave signal to be. And we're getting below the maximum theoretical limits on that, which says we could theoretically detect them in 04. If we'd been really lucky and we had some very deformed stars, we could have detected them already. Unfortunately, the lower bound on what those parameters could be is well below what we would be able to detect. So the closest we can have is a very optimistic maybe. So we're going to do the search and we're really hoping we'll find something, but we can't make any guarantees.
Great, thank you, Lucy. Then we have a question from George Dishman, which says, 04 has planned breaks for upgrades. To what extent do these disrupt long-term searches? What about the occasional short breaks due to loss of detector lock? So I think I can take this one. So these do happen, that you have these breaks due to commissioning, or you have just things don't work in the interferometer. But since these represent a fraction of the amounts of time that you actually observe for, your sensitivity doesn't decrease too much, and your methods have to be robust towards dealing with these kinds of on and off of the detector. And so really I guess the short answer is it does reduce sensitivity because you just have less data, but it doesn't really disrupt how we do the searches, because we have methods that are robust towards this effect. And so yeah, I think that's the short answer. Are there any other questions from any of the attendees? If there are, please feel free to write them in the chat. Yes, and thank you, George, for the response. So your methods are robust against loss of phase over the breaks. Yeah, this is true. And okay, so are there any other questions that any of the attendees would like to type into the chat? We have plenty of time for discussions about different aspects that may or may not have been clear, or that you want to know more about. Okay, Peter, thank you for your question. Maybe you could also put it in the Q&A, but perhaps in the meantime, I can read the question. Has anyone looked at the potential gravitational wave signature of a rotating naked singularity? I don't know the answer to this. I don't think so, but I'm not sure if any of the panelists would have a different answer to this question.
I don't think it's possible to add much to that, really. I think naked singularities themselves are speculative, right? And I think we can only sort of make concrete statements about emission from relatively mundane things like neutron stars. So no, I've never seen anyone talk about that in this sort of continuous wave context.
Thanks, Ian, for that. And then we have a question from Rafael, to which Aranova is going to answer. Are these slides available in the DCC or the Document Control Center? So please go ahead.
Hi, Rafael. I think it will be available in the DCC. It's openly accessible.
Yeah, that's correct. So we will post the slides in a public DCC entry, and all of this information will be accessible to anybody who would like to know more. Are there any other questions from any of the, oh, yes, there is, from Thierman Oliveira. When you analyze the data, do you know the direction that the data came from, at least some area of the sky? So I think, so perhaps I can also take this one. So for these types of searches that are for known objects, so you know the location of the sky location based on electromagnetic observations. And with this, you can basically point so you don't physically point the detector, but you point when you do the analysis of the data by essentially correcting for the Doppler modulation that's due to the Earth's orbit around the sun with respect to the location of the source. And so you do know, yes, you do know more roughly, or even better than roughly in some cases, where these signals would be coming from. And this is why you can take such, in the case of the known pulsars, you can take Fourier transforms that are essentially the length of the entire observing run. And in the case of the supernova remnants, you can take longer Fourier transforms than you could compared to an all sky blind search, which is what has been the subject of the past webinar. So the short answer is yes, we do know something about where the source is in the sky, and so we can use this to improve the sensitivity towards these sources. Okay, then there's a question from Garvin Yim. Which source do the panelists think the first CW detection will come from, e.g. spinning neutron stars, R modes, low mass X-ray binary? So I would like to give the panelists an option to answer this. Maybe we could start with Lucy or with Andres, if you wouldn't mind answering one of these questions.
Yeah. I don't know if I want to give an answer, because I feel like this is the kind of question that if I asked it at a conference with a bunch of LIGO scientists, I could start a bit of a big fight. I think personally, I'm behind just spinning non-axisymmetric neutron stars. I think R modes are a possibility, but we tend to do less searches for those. So even if they're more prevalent, I think we're probably less likely to see them first. And to further hedge my bets, I'm going to argue that LMXBs have gravitational waves because the neutron stars within them are spinning. So I win either way. So that's going to be my answer. Andres, did you want to share an opinion?
Yeah, I do agree that it's a difficult bet, but yeah, LMXBs does have a lot of potential. I think the downside of their searches are that, at least for instance, for Scorpius X-1, which has a high X-ray flux, so you will expect high or strong gravitational wave emissions, you have to search through let's say, very broad parameter space. So that makes this sort of search very difficult. So if I had to put a bet, I will say that probably if it comes from LMXBs, it would be from something like the AMXP search, where we have the same sort of physical system in some ways, but the parameter space is smaller. So yeah, if I had to bet, I'll say that.
Well, thank you. That sounds great. And maybe we can move on to the next question by George Dishman. You've shown results for the Livingston and Hanford separately. Can the signal to noise ratio be improved by coherent combining of the signals? So Lucy, could you please take this one?
Yep, so I'm assuming this is talking about the figures I showed where we had for one particular supernova remnant, we showed results from Hanford, Livingston and Virgo. And we showed the 3 interferometers separately because for that particular search method used there, it works best when you actually have the 3 separate interferometers, because we then apply a interesting test to any candidate signals that uses the distance between those interferometers to sort of assess, is this behaving like a gravitational wave or is there something here on Earth? There are other methods, and in that search we used 3 methods, and 2 of them combined data from 2 detectors and 1 of them didn't. I just happened to show the one that didn't, but we do often combine data from multiple detectors, and it does boost our signal to noise ratio. So great question.
Great, thank you. Thank you for that, Lucy. So then the next question is about how by Evangelos Simriniotis, and this is the question is about how would a pulsar continuous wave detection help constrain the neutron star equation of state? Arunuba, would you like to answer this question?
Yeah, sure. Hi. So that's an interesting question, so it actually depends on what type of signal we see as a continuous gravitational wave detection for the first time. For example, if it comes from Rossby wave oscillation, the thing that Ian showed, we could actually give a good constraint on the neutron star equation of state, provided we have a separate independent information about the neutron star spin frequency. For example, imagine an accreting neutron star or a neutron star that is shown in radio pulsation, in radio frequency, a radio pulsar, where we accurately know the stellar spin frequency. Now, R mode frequency is predicted to be around 4/3. In Newtonian gravity, it is just the 4/3 of the stellar spin frequency. But in fully general relativistic calculations, it actually has a correction over the 4/3 stellar spin frequency, and the correction term is dependent on the compactness of the star, that is the gravitational mass over the radius, stellar radius of the star, that's the compactness. And this quantity depends on the neutron star equation of state. If you change the neutron star equation of state for the same gravitational mass, you get a different stellar radii and thus a different compactness. And this introduces a correction term that is different for separate equation of state. And if you can measure this, you can detect this pulsation from R mode oscillations, you will very accurately measure the pulsation frequency of the R mode signal itself, and you will have an external information of the stellar spin frequency, so you get a good handle of the neutron star equation of state. Similarly, there are various other oscillation modes of the neutron star, F mode, G mode. Each of them can give a good constraint on the neutron star equation of state.
Okay, thank you, Aranuva. And the final question was answered by Win in the chat, or by typing. And so, have you tried to check t-square values from neutron star binaries? So yeah, the short answer is yes, we have. So and we have run some methods for it, but I think at this point we are out of time. So I would like to thank all of the panelists for being here and providing very good answers to questions, and the speakers for providing us with very interesting presentations about this very important work that LIGO Virgo and KAGRA are doing. And I'd like to thank all the attendees for asking very interesting and very, very good questions. So stay tuned for perhaps the next webinar that of course will be announced at some point if there is one. So Thank you all for coming, and we hope to see you at the next one when it happens. Thanks.